All right. Overall, we're just supposed to be investigating polynomials. I mean, we can break it down into all the wonderful objectives that we have here: graphing polynomial functions, distinguishing that end behavior, finding the zeros, using the intermediate value theorem, and modeling polynomial functions. But when it comes down to it, we're trying to graph polynomial functions with as much information as we possibly can, and using the graphing calculator when we have to, which, for polynomials of higher degree is usually all the time, because it's putsy to sit and put numbers in when you have 4 or 5 terms with the x in there. So yesterday we finished up talking about how when you have a cubic, it should have 3 zeros. That doesn't guarantee they're all going to be real. You might get one real one and 2 imaginaries, things like that. But we know they're there. And it will have 2 turning points. And a quartic should have 4 zeros, real and or imaginary, but 3 at most turning points. And that is not a shocker from what we learned in the past in Algebra 2. And that came from a little formula that we used called n-1 to find the turning points. So if you know the amount of zeros, which you should by looking at the polynomials, see what the degree is, then you can go ahead and subtract 1, and that should tell you how many turning points it may have. Because remember, there might be none. I mean, we've had cubics that have had no turning points. But it's also possible that there's 2 because the cubic comes up, goes back down, and makes the sign changes to get back to that normal end behavior for cubics. And it will have at most n zeros. So your degree should be telling you how many zeros you can find. But yeah, they're not all real, and if it's something that's not factorable, you might not be able to find them all. But we'll do what we can. So this next portion is what I was talking about yesterday when I said some people have struggled with the end behavior stuff before, and I was thinking, how is that happening? And then I remembered some people have come from college algebra. And if you came from college algebra the year before, you maybe had a teacher that described, I think we have 1 or 2 teachers that describe end behavior as just up and down. Well, at this level, we don't do that, so I've got to retrain you on this. But what I'm going to have to do is just go after this a little bit slower than maybe I have in the past. Those of you that already know it, yeah, it'll be a little slow for you, but that's okay. I want to make sure everybody gets this. That's the whole point. So when we talk about end behavior, we always use the same template for writing end behavior, and that is the limit as x approaches negative infinity of f of x equals blank. So we write that down every time exactly that same way. And what this is saying is, as our x's go to negative infinity, so they start at 0, 0, and then they go off to the left forever, what's the graph doing? Is it going up or is it going down? So our job is to figure out if it's going up, that we're going to put infinity in here. And if it's going down, that we need to put negative infinity in here. So you start at 0, 0, and you just kind of read your graph. Is it going up or is it going down? Going to the left. And then, of course, we have to go on the other side and say the limit as x approaches infinity. 20 years ago, just 20 years ago, we used to put positive infinity on there. But over the 20 years, last 20 years, people said, well, that's kind of silly because infinity is positive infinity. And the fancy word for that is it's redundant. So they decided we're not going to put the plus in there anymore. We're just going to leave it as infinity. But that's the only change in our template. Because that one's saying, start at 0, 0, go to the right forever. What is your graph doing? Is your graph going up or is it going down? So this is what we'll write down every time it asks for end behavior. But what we have to do is figure out, should we be putting positive infinity in here? Or should we be putting negative infinity in, and which one gets which? And it could be they'll both be positive infinity or they'll both be negative infinity. It could be we'll get one of each. So this is how we really write end behavior. But because we have lots of them, we're supposed to do in this example, and we would be spending all of our time writing that end behavior, what we're going to do is we're just going to put either positive infinity or negative infinity, and we're going to work with the number line. We'll do the left first, and then we'll do the right. So the This says graph each function in this window and describe the end behavior using that limit notation. I do need to let you know that Pearson books are backwards. If you look at this, you'll see they've got positive infinity first and then negative infinity. It's just something with Pearson publishers. Know that that's not correct. We want to make sure that we're doing negative infinity first and then positive infinity so that we stick with the number line. Well, if you look at these, you might get a little overwhelmed until you remember. If we have an odd degree polynomial, they all behave as an S-curve. So if it has a positive leading coefficient, it's going to look like this. And you can think for a second about the fact that this graph would be going through 0, 0. Well, that means from this point, as we go to the left forever, this graph will be going down. So we'll want to put negative infinity in as opposed to the left. This graph over here, well, the same graph, as we head from 0, 0 to the right forever, would be going to positive infinity, going up. But if we put a negative in front of that, then it reverses. So from 0, 0, kind of the center of that graph, going to the left forever, we're going to have infinity. And then as we go to the right forever, from the center of the graph, we'll go to negative infinity. So it doesn't really matter whether or not it's a 3, or a 5, or a 7, or a 9. That end behavior is what we're going to get. Now that's not true with even degree polynomials. And that's because even degree polynomials behave parabolically, which means their end behavior is that of a parabola. So if we have a positive leading coefficient, then we should be able to put infinity and infinity. Because again, with our parent function, 0, 0 would be down here. So as we go to the left forever, our graph is going up. As we go to the right forever, our graph is going up. And then a negative leading coefficient gives us downward opening parabola. So that one would be negative infinity and negative infinity. So as I was saying earlier, you just have to visualize what the graph is going to look like. And then say, oh, this side's going up, this side's going down, and just think your way through it. And then translate up and down into infinity and negative infinity. So 1a says 2x to the third. So I think, okay, odd degree, cubic there, odd degree, and it has a positive number in front of it. So that's going to go down as I go to the left forever, negative infinity. And as I go to the right forever, positive infinity, which again we just write as infinity. So negative infinity and infinity. I go to b, and it says f of x equals negative x cubed. Because these are goofy, they go across. That's probably going to throw some people off, but a and then b. Negative x cubed. Okay? This picture in our head. Well, this time it's going to go up as it goes to the left and down as it goes to the right. So infinity and negative infinity. I go to C. It says x to the fifth. Still going to be odd degree, positive leading coefficient, negative and positive. D. Negative 0.5x to the 7th. I really don't even need the 0.5. I just need it that it's negative and it has an odd degree. So this will be positive infinity and negative infinity, which is infinity and negative infinity. There it is. Going to 2. I want you to help me more. So looking at 2a, negative 3x to the 4th. What should we put down? I need to warn you, I've been waiting for my order of little duckies. Put your names on so that I can just pick them out and we can do a non-volunteer thing because you guys have not been talking enough. And my duckies came yesterday. I'll just write your names on the duckies. Pull them out of a bucket or something. Just come on. You're not talking. You have to talk. You have to talk about this stuff. It'll help you out a lot. 2a. Negative 3x to the 4th. Where's it going? Negative and negative. Good. 2b says 0.6 x to the fourth. What do we have? Infinity, infinity. And if you say positive infinity, I know exactly what you're saying. We'll just, it's actually a good habit to get into. Negative infinity and positive infinity. 2c says 2x to the 6th. What you doing? Infinity and infinity. Which makes you feel like you did something wrong because it's just like going above it, but no. And then d is negative 0.5x squared. What's that doing? Negative and negative. So I want you to go ahead and do 3, and then normally I do candy partners, but we only have 36 minutes today, so I'll have you chicken wing and elbow partner when we get 3 done. Check in with somebody. Make sure everybody's getting the same stuff. All right, you quiet people. It's a requirement. You have to chicken wing and elbow partner. Show somebody your answers. Got them? So what'd you have for 3a? Infinity and then negative infinity. 3b. Negative and negative. C. Positive. And D. Negative and positive. Here it is. So that's end behavior. But again, if we write this in the homework, we're going to have to go back and use our template. Limit as x approaches negative infinity, f of x equals blank. Limit as x approaches positive infinity, f of x equals blank. And then everything will be fine. So, end behavior. 43210 means just got end behavior. Where's everybody? Good, because I think some of you were a little rusty on this before, but now you should be set. So, on to the next piece, which says we're going to compare the graphs of a polynomial and its leading term, which is kind of what we were just doing. Superimpose the graphs of this monster and then this little parent function in successively larger viewing windows, a process called zoom out. Continue zooming out until the graphs look nearly identical. So grab your graphing calculator. And with that first monster up there, we know what to expect of the end behavior. But this negative 4x squared minus 5x minus 3 gives it what I call lumpy bumpies. There'll be some turning points and things in that one. Not in x cubed, but in that first one. So go ahead and put those in. And I'm going to have us do a little bit something different. Watch this. Ready? You can actually change on all of these, I believe. I know the color ones you already have. You can tell the difference between your two graphs. But for the rest of us, if we go all the way over to the left on the x cubed graph, so you're going to hit the arrow 1, 2 times. You can change the look of what's graphed. And I've got the bouncy ball and a line following behind it. So I think you have to hit up here like 4 times. But I'll get back to where you guys are at. Oh, fantastic. These look like that. So enter makes it thicker. Then we have shading. and more shading. And then we have the one we want, which is bouncy ball. So when we graph that one, what we're going to see is a little bouncy ball, slowing it down a little bit so we can make sure we see it, and it'll have a line behind it to show us what the graph is. So we'll try zoom 6 first. So there's the one with the turning points, the one we want. And there comes bouncy ball, just slowing it down a little bit to show us what's going on. Now, for me, I mean, that definitely shows that the end behaviors are the same. But they're saying if those turning points are kind of bugging us, what we could do is we could hit zoom and then number 3. And just hit enter at 0, 0. And when we start making this window bigger and bigger, you'll notice how it seems like those end behaviors are getting closer and closer together. In fact, the one that's going down right now almost looks like it's one curve coming together. And if you zoom out one more time, so zoom 3, one more time, they will just almost look like vertical lines. So that turning point business kind of disappears as you keep increasing and zooming out that window. And that's because if you think about what's going on, when we're zooming out, we're putting in bigger numbers. And if you're going to put bigger numbers into this first equation, this x cubed is going to take over. I mean, numbers get big really fast when you're talking about cubing something. So the rest of this, yeah, it's going to create turning points, but we know we're going to come back to that end behavior. So what do we notice about the end behaviors of the two polynomial functions as we zoom out? They are the same. And we should not be shocked by that information. They are the same. Because insufficiently, hard to say this name, insufficiently large viewing windows, the graph of a polynomial and the graph of its leading term appear to be identical. And again, that's because that highest power, the degree of the polynomial, kind of takes over as you get to really big numbers. So the leading term dominates the behavior of the polynomial as our x's approach. As we get bigger and bigger values, it's going to happen. Now this little box down here is very similar to the shapes that I gave you when we were talking about end behavior. You know, it's just that these have some turning points in there. End behavior, you don't think about the turning points. You think about what is this graph doing as you go to the left forever and the right forever. So if we have a cubic, as it says n is odd here, and the leading coefficient is positive, this arrow is going down and this one's going up. It's great that they showed us this these turning points inside here, but they're showing it dashed because they want us to know that's not what's important when you're talking about end behavior. And same thing over here. They've got a negative leading coefficient with an odd degree, but don't look at the dashed stuff. Look at what we care about. What's the behavior as we go to the left forever and the right forever. And then a couple of quartics that follow exactly what we were talking about before. So no shocks there. And down here it says applying that polynomial theorem, which is our objective. We want to apply all the stuff that we learned about this to graph our polynomials. So we're going to graph the polynomial in a window showing its extrema, local maxes, local mins, those turning points, and zeros, and its end behavior, and describe the end behavior using limits. So first things first, I would want to do whatever I can do algebraically and by hand before I pop it in the graphing calculator. So I look at this and I say it's got 4 terms. The only way you guys have learned to find zeros with 4 terms would be factoring by grouping. So if we group this, we could pull an x squared out of those two and a negative 1 out of those two, and we have a problem. Because you can only factor by grouping if those parentheses come out to be the exact same thing. And they're not the same thing. So, disappointingly, that means we have to hand this over to the calculator. We don't have the algebra skills at this point to do anything more with that. So, we tried, didn't work. We're going to have to grab a calculator. So let's punch her in and see what happens. Let me get my parentheses out of the way there so you can see them again. So I am just deactivating the graphs that I did with you earlier so that I could just graph plus 2x squared minus 11x minus 12. And back to Zoom 6. Well, I can't use a negative 10 to 10. It's not showing all the stuff. I have to see that local max and that local min. Well, the local max, that's not that far off. So in my window, maybe I'll change this from negative 10 to negative 20 to 20. Try that. See if I can see all my x's and y's. Almost. Dips a little bit farther than negative 20. So maybe negative 25. Seems like a really small step, but what that just did was it told me I can't go by ones on the one when I graph this, or I'm not going to be able to fit all the good stuff that I need on there. So if it goes down to negative 25 and I only have a grid of negative 10 to 10, probably better do something like going by threes. That way I'll be able to see everything. So my y values, and there's a little 3 there to let people know, hey, that's going to go by threes. But I'm going to label my x's with a 1 so they know I did not change anything on the x-axis. I am just changing the y-axis. That's all I'm doing. And because we have to hand this over to the calculator, we are probably going to need more points than we would normally do. So our table is probably going to be pretty large. Second table. All right, well, I'm not graphing negative 7, negative 180. I don't know about you, but I'm not putting that on mine, or negative 6, negative 9. But I'll probably write down negative 5, negative 32, so that I know, this is going to be almost straight down, negative 5, negative 32. And then I've got negative 4, 0, which would be nice, because we were supposed to identify those zeros there. Negative 3, 12. Negative 2, 10, negative 1, 0. And we've got 0, negative 12. 1, negative 20. 2, negative 18. 3, 0, 440. And I'm going to write down the 440, but obviously I'm not going to graph that. But why not? Oh, she did. Okay, yes. Alrighty, let's get this graph. We've got negative 4, 0, so 1, 2, 3, 4. And then I know it's going to go down to negative 5, negative 32. So that's pretty steep down there. And then I have negative 3, 12. So negative 3, 3, 6, 9, 12. Right there. Negative 2, 10. 3, 6, 9, and a little more. Negative 1, 0. 0, negative 12. 3, 6, 9, 12. 1, negative 20, so there was 12, 15, 18, more. 2, negative 18, 3, 6, 9, 12, 15, 18, 3, 0. And then 440, so almost straight up from there. Well, why didn't I just connect everything up? Because I don't know. Up there is the local max and the local min. That's why I didn't just connect it up. I've got to go back to my graph and let Blinky tell me where is local max of blank at x equals blank. Local min of blank at x equals blank. Got to hand it over to the calculator. This part we will have to all year long, and that's because it requires calculus in order for trace number 4. Put Blinky to work. Left side, right side, enter. 12.597 at x equals negative 2.694. Okay, so let's see. Negative, not quite 3, 1, 2, not quite 3, 3, 6, 9, 12, and just a little bit more. So now I'm confident that's that highest point right there. And then second trace, number 3, I need left side of the valley, right side of the valley, enter through guess, negative 20.745 at x equals 1.361. So, 1 and just a little bit more. And let's see, this one was negative 20, so it's going to be just a little bit more than that before it comes back up. So now we've got it accurate because, bless you, we got some zeros over here from the graphing calculator because it wasn't factorable by grouping. And we found our extrema, and we just used the graphing calculator to give us the rest of the stuff. The one last thing they wanted us to do, end behavior. Limit as x approaches negative infinity, f of x equals like. Limit as x approaches infinity, f of x equals blank. So there's our template. Like I said, we're going to write that every single time. The only thing different is going to be what we put in the blank. So as our graph went to the left forever, where's it going? Down, negative infinity. As our graph went to the right forever, where's it going? Up, positive infinity. Now that's putsy, and it takes a while, but we hand it over to the graphing calculator, and the reason I say that is because B is a quartic that is super putsy because it has 3 turning points. So I'm going to 43210 you on how you feel about using your graphing calculator to find the max and the min and all that good stuff. So show me your numbers. I'll know if I can skip the quartic. All right, looks like everybody's pretty confident with the graphing calculator. Yes, then we can just skip the quartic, which is very putsy, and go on to this, where we say, hey, algebra, maybe we can do this one with algebra. Finding the zeros of a polynomial function. Find the zeros of blah, blah, blah. Here's a big step. Seems like a little thing. You're finding the zeros. It has to be 0. It is a big step. That says, hey, I know what I'm doing here. So does going through the list that we use for factoring. And the first thing we always check is there a greatest common factor we could pull out of all of this? What do you see? Take an x. Then we'd look for perfect square trinomials. Is that a perfect square trinomial? No, a negative 6 in fact is not. But that doesn't mean that there isn't some good old-fashioned factoring we can do to get two numbers that multiply to negative 6 and add to negative 1. What are they? Negative 3 and positive 2. So if we know that, we should be able to write down our zeros. What's the 0 for this little bugger? 0, so that'll be 0, 0. How about x minus 3? 3, 0. X minus 2, or sorry, x plus 2. I hate when I say the answer. I'm trying to go through these. Negative 2, 0. There it is. So we've got our zeros, and like it says, how long is it going to take to punch this in and then check your table and make sure that the zeros are where they're supposed to be? So support it graphically by punching in x to the third minus x squared minus 6x. Little zoom 6 or graph action there. Second table. And we said negative 2. Well, look at that. We said 0, 0. Fabulous. We said 3, 0. Yay, us! Got it. So supporting graphically is just, take a quick look, pop it in your graphing calculator, make sure that those zeros are where you said they were supposed to be at. So when we can factor these, we absolutely want to do that. We want to show the math by hand so that we can say, yes, I know what I punched in the graphing calculator is right. So now, reminder, we do get repeat zeros. Sometimes we factor and we do get a perfect square trinomial, and that means we'll get x minus 3 squared. Those are said to have multiplicity. Root word of multiplicity, multiple. That's why if it just shows up as a first power, we don't say it has multiplicity. It has to be there at least twice, 3 times, etc. So if f is a polynomial function and x minus c to the m is a factor of f, but x minus c to the m plus 1 is not, then c is a 0 of multiplicity m. So if you see a 2 up there, you see a 3 for the power, 4 for the power, then you say it has multiplicity. This one is multiplicity 2. Anybody remember what that tells us about the graph when your 0 has a multiplicity that is even? It means it's a tangent. In this case, what's going to happen is 1, 2, 3. Our graph is going to hit at that 0, 3, and it's going to bounce off. Now, that's not the same tangent that you have for SOHCAHTOA, but it's a different polynomial type of tangent that we have. So, if we see an even degree, it's a bouncer. It's a tangent. But if it is a normal first, third, fifth, any kind of odd degree, then it's going to cross. And that's what this box says. It says if a polynomial function has a real 0 of odd multiplicity, then the graph of f crosses the x-axis at that 0, at C0. And of course, the value of our y's go from negative to positive or positive to negative as it crosses that 0. And then if a polynomial function has a real 0 c of even multiplicity, well, that's a bouncer. And most books call that a tangent. This book, I think, is worried that you're going to confuse that with SOHCAHTOA. So they just say, does not cross the x-axis. But that's our tangent right there. So odd powers, crosses. Even powers, bounces. It's a tangent. All right, and we're down to 16 seconds. So you should probably be able to do both 2, 3, day 1 and day 2. We did not get to the intermediate value here. Take a picture if you need to, but I will save these and put them on Schoology. In fact, I already did the first hour. You are going to third hour next, but then remember we skipped fourth hour, third, fifth, sixth, then